Hello and welcome back to the Mole Vodcast number 4. This is Miss Carr. We're going to be talking today about how to go through multi-step mole conversions. This is a little bit different from the single-step conversions that we've been doing so far, but if you follow along with me, you will notice that nothing that we're doing is any more complicated than the simple single-step mole conversions. You're just doing it more than once. So let's go ahead and get started. The trick to multi-step mole problems is that if you're given a problem where you have grams or liters or number of particles and you don't want to convert them to the mole because that's a single step mole conversion, how many grams in a mole, how many moles in this many liters, how many particles are in 3 moles of this, then you have to perform a multi-step problem and you actually use the mole in the middle. So the whole idea is if I want to go from grams to liters, then I need to go grams to moles to liters because I have a conversion factor for grams to moles and I have a conversion factor for moles to liters. What I don't have is a conversion factor that goes directly from grams to liters. So if I want to go grams to liters, I need to go grams to moles and then moles to liters. It's like being able to convert something like seconds into years. I can't go directly from seconds to years because I don't know how many seconds are in a year. But I can go seconds to minutes, minutes to hours, hours to days, days to years. So that is a multi step. Now, the multi step problems we're going to be dealing with aren't even as complex as that. So, if you can figure out how to determine the number of seconds in a year, then you should be easily able to determine how many grams or liters or particles there are in a gram, a liter, or a number of particles. So if we take a look at an example of this type of problem, you would say if I have had so many liters of oxygen gas and I want to know how much it weighs, you would have to first find how many moles are of oxygen gas you have. Then you can find out how much that many moles of oxygen gas weighs. Because of course we know the molar mass of oxygen by looking at the periodic table, and it tells you how many liters of oxygen gas you have. Now, at this point, you do need to go back and review those 3 conversion factors that I told you that you had to memorize. And that is that there are 22.4 liters of gas in a mole, and that the number of particles in a mole is 6.02 times 10 to the 23rd. Okay. So if we know how many liters of O2 we have, we can determine how many moles of O2 we have because of course there are 22.4 liters in a mole because oxygen is a gas. So we can go moles of O2 to grams of O2 by finding the molar mass of O2, which tells us how many grams 1 mole of oxygen weighs. Okay. So for an actual example, we're going to throw in a number here. We're going to throw in 13.9 liters. So how much would 13.9 liters of oxygen gas weigh? The first step is that we want to take what we have and, of course, convert that to moles. Then we take the moles and convert that to what we want to have. So over here, what we have, liters of oxygen gas, moles is our intermediate step, and then grams is what we want. So what you have on the left, sorry about that, what we have on the left, what we want on the right, and moles in the middle. Okay, so if that's how you set up this problem, we can go ahead and throw our numbers in to our dimensional analysis. We start out, we have 13.9 liters of oxygen, okay, and the first step in our dimensional analysis is to turn that into a mole. So we have 22.4 liters of oxygen is equal to 1 mole. That's our first equality that we need to put into that dimensional analysis. Then we want to go from having moles to have. Okay, and if we want to be able to convert our moles, which is what we have currently using this single step conversion here, then we want to be able to convert those moles into grams because that's the second step of our two-step process. And of course, we need to find out how many grams are in a mole of oxygen. So we need to go back to our our vodcast number 2 where we discussed molar mass. And so we need to define the molar mass of oxygen, how many grams of oxygen are there in a mole. So we have O2, which is two oxygens. That is, one oxygen is 15.999 grams. We need to multiply that by 2. Please correct this. This is a mistake. It should not be 1, it should be 2. Which is 2 times 15.999 gives us 31.998 grams per mole of O2. So if we put that in our equation or our dimensional analysis as an equality, we have 1 mole of O2. We put that on the bottom because we want to cancel our moles out. So we have a mole up here, we have a mole down here, and that's going to cancel. So what we want to put up here is the last thing that we're looking for in our problem, and that's our grams. So if we put in our molar mass, and we of course multiply across the top, divide across the bottom, we will find that our number of grams of oxygen in 13.9 liters is going to be 19.9 grams of O2. And of course, we put that in the same number of significant digits as we had in our original information that was given to us by the problem. So you round that to 3 significant figures, and that will be your answer to that problem. Okay. We're going to take a look at another example here, and that would be going from molecules to grams. So, of course, you don't know how many molecules are in a gram of a substance. It looks like we have 35.43 grams of CO2, that's carbon dioxide. So, what we do know is we know how many grams are in a mole, and we know how many molecules are in a mole. So, we can use our equalities from the last vodcast when we were doing single step conversions, and we can do 2 single step conversions in a row to get us to where we need to be. So we take a look at how many molecules, that's what we want to know, and what we have is grams. So we start with grams. We will need to convert those eventually into molecules, but we need to go through this intermediate step of converting them into moles. So moles kind of becomes your go-between when you're doing these problems. Okay, so we take a look at what we have. We put that in the upper left-hand corner of our dimensional analysis. We have 35.43 grams of CO2, and we want to convert that first into moles. So in order to do that, of course, we need to find the molar mass of CO2, right? We find the molar mass of CO2. We have one carbon atom at 12.011 grams. Then you have 2 oxygen atoms at 15.999 apiece. So your grand total is going to be 44.009 grams per mole. So you have your roughly 44.09 grams of CO2. We want to put this on the bottom in our dimensional analysis, and the reason for that is, again, we want to be able to cancel these grams out. So we no longer want grams, we want to convert it into moles. So this 44.09 grams of CO2, of course, is equivalent to 1 mole. So we put that there on the top of our dimensional analysis. Now, once we have this, we have the moles of CO2. But again, this isn't what the problem is asking you. It's not asking you how many moles of CO2. It's asking you how many molecules. So then you have to pull out your equality. How many molecules are there in a mole of CO2? Well, the same as the number of molecules of anything in a mole, which is, of course, 1 mole of CO2 is 6.02 times 10 to the 23rd particles or molecules of CO2. Okay, so that will give us a grand total of 4.84 0.46 times 10 to the 23rd. Again, the reason we round to our four significant figures is that's what's given to us in the problem. If you're given four significant figures, you end with four significant figures. So 4.846 times 10 to the 23rd molecules of CO2. So again, it's very similar to the single step conversions. You are just going one more step. You're just doing another conversion. It's like two conversions in one. Two conversions for the price of one. Okay, we're going to do one more example. What I would like for you to do is pause this and try to work this example on your own and see if you can at least set it up, even if you can't finish working it. See if you can get the setup correct. So the question is, how much space or volume would 2.84 times 10 to the 23rd molecules of hydrogen gas occupy? Hydrogen gas, of course, is the diatomic. It's H2. So go ahead and pause the video right here and try to work this problem on your own. I'll be here. Okay, your first step, of course, is to figure out which equalities you're going to need. And so you want to set up what you have versus what you're trying to get to. So we set up what we have, which is particles of hydrogen gas. Then we set up what we want, which is how much space. We're looking for volume. So we know that we can't go directly from particles to volume, so we have to go through our intermediate step of moles. So we say particles of H2O converted to moles of H2, or not H2O, H2, moles of H2. Then we convert to liters of H2 because we have the conversion factors that will help us do these steps, going from particles, sorry about that again, going from particles to moles, and then we have the conversion of going from moles to liters. And those are conversions that you need to have memorized. Those are the equalities I told you to write down in your notebook. So make sure that you do know the particles to moles, which is of course always 6.02 times 10 to the 23rd. Then moles to liters, which is always, when you're dealing with a gas, is always 22.4 liters. So we set up what we have. We have the number of molecules of H2. Then we need to convert that into moles. Okay, of course we have molecules for 1 mole of H2. Remember, you put what you have on the bottom so that it will cancel out, because we don't want molecules anymore. We want to get rid of the molecules and change those into moles of H2. Then we can put number of moles of H2 and the volume of gas, which is our conversion factor here for how many liters that much hydrogen gas takes up. And that is 1 mole of any gas is going to take up 22.4 liters. So for this one, we never had to find the molar mass because it asked nothing about how much it weighs. So we just had to use the equalities that we already knew, and there's no calculating of our molar mass here. And we're left with 10.6 liters of hydrogen gas. All right. If you're having any trouble with this, please make sure to come and see me either during class or outside of class. And I will see you for vodcast number 5.